Okay, so today we're going to continue talking about the insides of stars. So how's everybody doing? Did y'all have okay weekends? All right. Everybody raged all night?
Yeah. Yeah, I went to the rave. Yeah, you know me. 3 nights in a row. You know how it is, rave on the weekends.
So today, let's see what we're going to talk about. So we're going to go, okay, so there are no more readings, so I haven't gotten a chance to change the reading schedule. There are no more readings due before the test next week. There's a homework due though, okay? So, so there's going to be a homework due Monday. It's not up yet. I'm going to put it up maybe today, probably tomorrow. I've got a grant due, and that
I think it's
kind of
up
takes
already.
the assignment is up, but there's not actually an assignment in the assignment.
Oh.
So it's been up for a little bit. There's been an assignment there, but there hasn't been actually any work in it. So so it's going to be due Monday, and then Monday we'll also review for the test. Let's just call it a test. It's not mid anything anymore. So it'll be a test on Wednesday.
It's a 3/4 term.
Yeah, it's a 3/4 term, whichever. Some partial term. Partial term's not a good term for that. So we'll have a test on Wednesday, and it'll cover, so nominally it's going to cover the new stuff, but it does stack, so there's not really any way to avoid it being a little bit cumulative. But I'm not gonna do anything obnoxious like ask you to derive Kepler's laws again on this test.
Feel free.
But I might on the final. Oh no, don't worry, I will on the final.
You're gonna have fun.
All right, guys. All right. Okay, so test on Wednesday, homework Monday, office hours Thursday. So plan ahead a little bit. So if you could read the homework as soon as it comes out, so that you know what questions you have for office hours, that would be awesome. So that you know that whether or not you need to go to office hours, because I'm not holding office hours over the weekend. But the homework is due Monday at 7 a.m. or whatever. So it's formally midnight on Sunday. So work on it on the weekend. Don't work on it on Monday. Okay. So today we're going to finish up stellar interiors. So we're working on generating and deriving the equations for stellar structure and evolution. So the equations for stellar structure and evolution look like this. dP, dr. So this is how the pressure changes with why am I writing over there? I'm writing over here. No, I'm going to write over there because I want to leave these things up. Oh, and that's totally not legible because the camera's too far away. That's all right. dP dr equals minus g m of r. Okay, in the book he has the subscript r. That means it's a function of. It's just saving a couple of characters by making it a subscript. P is a function of radius. M is a function of radius. It's just shorthand, right? I mean, I could write these parentheses here, but that doesn't get anybody anywhere. M of r. So m of r times rho times r to the minus 2. Okay. How do we get this? This is just balancing forces. So dP dr is the force from the pressure gradient, and gm rho over r squared is the force from gravity. So this was familiar. You've seen this one hopefully partially a couple of times. dm of r dr is 4 pi r squared rho. Think about this just like a 3-dimensional volume integral. That's just 4 pi r squared from the volume integral. And we're just taking a derivative of the volume integral. That's what this says. And then the two that are, so these two are relatively easy to get. And then the two that are hard to get are the temperature gradient and the luminosity gradient. So the luminosity gradient I haven't derived yet, but I'm going to. But it's actually very easy. Luminosity, actually let me do it real quick. I'll do it over here where I'm doing active stuff. Yeah.
Can you label the top two?
Yeah, this is pressure. Well, they're labeled by the first thing. This is the pressure gradient. This is the mass gradient. So all of these are d something dr. Right? So this is force balance. This one is mass conservation. This one is energy production. And this says that dLdr is 4 pi r squared rho. Hey, that's pretty familiar. Epsilon, that's the production rate. And epsilon is a function of radius and temperature, so this is a complicated thing, and this takes a while to actually get epsilon. But it's just a function of the local thermodynamic properties, so it doesn't need a differential equation, because it doesn't depend on the structure of the star. So this is energy production, and I'll derive this in like 30 seconds. And then energy transport. We write this as a temperature gradient, but really it means how the stuff is going to move. Because why? Because stuff moves from hot to cold, right? That's it. Stuff moves from hot to cold. So when I have a temperature gradient, stuff's going to go towards the cold. dTdr is, okay, depending on if you're in the convective regime or in the radiative regime, and I'll get to what I mean by both of those things in like 2 minutes. If you're in the radiative regime, then this is equal to minus 3 over 4a c. Yeah, my handwriting is small and terrible. Kappa bar, the Rosslin mean opacity. Now, you don't remember what the Rosslin mean opacity was and like its derivation and all of that stuff, and there's a d plot, dt, I don't know, it doesn't matter what it is basically the effective cross-section when you account for all of the other atomic lines that you could possibly take. So it's the effective cross-section of the thing with all of the details swept under the rug. Makes sense? So the Rosslin mean opacity times the density times t to the minus 3 times L of R. So this is radiative. Or minus 1 over gamma mu mp over k. If this is just a number, this is just a units thing. Gm over r squared. And this is convection. Okay. So I'm just going to leave those guys up there. And so we've derived the first two. We started deriving the last one. I'll derive energy production real fast. So let's derive that. So dl, this is a little bit of energy production, so a little bit of luminosity, a little bit of change in luminosity, is going to be epsilon, which is my burning rate. So this is the burning rate in per kilogram, or perhaps joule per kilogram, times kilograms. Does that make sense? So this is just stuff per mass, and this is just the mass. Very easy. What is dm? dm is just 4 pi r squared rho dr epsilon. So we can move this dr to the other side. dl dr equals epsilon rho times 4 pi r squared. Does that make sense? So now this epsilon is a headache, and we'll talk about how to get epsilon a little bit today, but I'm really going to spend Wednesday on it. So that's that equation. So this is the energy production equation. Now we need to get the transport equation, which I'm going to finish today, and then we'll talk about epsilon. So I'll finish convection, and then we'll do energy production. Is there anything else I need to do? Everything there is sorted. Sweet. Moving on, not that one. This one. And I don't need that one. Okay. So this is all thermodynamics. So I'm just gonna write down du equals dq minus p dv. This is my first law. I'm only writing that down to get brains started on thinking about thermodynamics. We're not actually gonna use that. So one of the things that we proved is that when it's adiabatic, that means that dq equals 0. It also means the process is fast. I'm gonna put fast in quotes because fast is relative to the problem. It just needs to be fast relative to the heat transport. So your process needs to be quicker than the conduction time scale. We don't need to worry about the conduction time scale, just think about fast. So when it's adiabatic, the heat flow is 0, it's relatively quick. What I know is that P equals some number rho to the gamma. And this constant is like P naught over rho naught. It's like your initial condition. So I'm gonna look at two things. So what am I actually gonna do? So when does convection happen? Convection happens when the temperature gradient is large. So that means that there's heat on the bottom, but not heat on the top. So something wants to rise up, so a little blob of fluid will get hot and rise up. That's the convection that we're gonna solve for. So what we're gonna do is we're gonna find a condition for when does something start to rise. So we started talking about this. When does something start to float? So we had started this on Friday. When does something float? Then the surrounding medium, right? So we have a bottle, and we're gonna just assume that this is some radius of the star. So we're gonna have a little blob of fluid that we're gonna raise up to be up here, right? So I'm gonna have two systems. I've got the star, so I've got the density of the star, I've got the pressure of the star, and I've got the temperature of the star. And these are all functions of radius. And radius in this cartoon is going up this way. Pretty good. And then I have also the density of the bubble, the pressure of the bubble, and the temperature of the bubble, which are also functions of radius. So we're gonna have a density for the bubble initial and a density for the bubble final. I'm not gonna write the final, I'm just gonna write density of the bubble. The initial condition is the initial, and this is a variable. It's whatever I want. So I'm gonna have a density, a pressure for the bubble, and a temperature for the bubble up top. So we'll have rho of S, rho of Si, so this is the initial conditions. P of S and P of Si, this is the initial pressure down here. And then we'll have P of Bi and P of Pi and T of Pbi, so we'll have an I for all of these things. So now we need to write down some differential equations for this. So actually, let me do this a little bit more clear. So I've got two states that I'm thinking about. Down here, my initial state, I've got rho I for the star, I've got Pi for the star, and I've got Ti for the star. That's what the star is down here. And I've got rho B initial, so that's what the bubble's initial density is. PB initial and TB initial. That's the initial pressure, temperature, and density for the bubble. Does that make sense? I'm gonna set these equal to the star because everything's the same, right? I'm just taking out a little bit and raising it up. So then up here, we're gonna have rho of the star, T of the star, and P of the star up here. And we'll have rho of the bubble, T of the bubble, and P of the bubble up here. So, okay. Let's think about the star for a second. So, P equals rho K over M mu MP T. This is the ideal gas law. actually, let's not think about that for a second. Let's think about, I'm gonna bring my bubble up here to this higher place, but I'm gonna do it quickly. So that process is adiabatic. Does that make sense? So because it's quick, heat doesn't flow. So it's not gonna equilibrate thermally with the bubble. It will equilibrate in pressure. So the pressure of the bubble and the pressure of the star are the same up here, but we're gonna forget that for a second. I'll come back and use that later. So for the bubble, I can write down that dP dr, because I know this is an adiabatic process, this is true. So dP dr is just a gamma comes down and I'm left with a gamma, and then I've got a k rho to the gamma minus 1. But this is just k rho to the gamma over gamma, that's what the minus 1 means. So this is just p, so this is just gamma p over rho. Does that make sense? Why I can get that dPdr is gamma p over rho. For the star, dPdr is, well, okay, we need to look at P equals rho K over mu M T. So dPdr, we're going to hold the concentration fixed, so mu is fixed. dPdr is just P over rho d rho dr plus P over T dt dr. Okay, does that make sense? This is just chain rule and product rule, yeah.
Is that the partial derivative d or normal t?
Which one?
The for those.
Everything here is, everything in this sentence, this is a full derivative, and this one is, actually this is a full derivative because, R is the only free parameter. So these all count as full derivatives right now. So, this is true for adiabatic. So for, oh, I'm sorry. I totally cocked this up. d rho dr. I skipped that bit. That's the rest of the chain rule part. Does that make sense? No? Yes? All right. So dP dr, just from this, is just gamma p over rho d rho dr. And for the star, dP dr is p over r d rho dr plus p over t dt dr. So this one is more complicated because here I get to assume, for the bubble, I get to assume it's adiabatic, so I have another equation that I get to use. They both follow the ideal gas law. So let's solve this for dP dr. Solve for this, and we'll plug into here. So this gamma's got to go over here. 1 over gamma. So we plug that into here, and we're left with dP dr equals 1 over gamma dP dr plus t over t dt dr. So then we solve this for t, or for the temperature derivative. dt dr equals 1 minus 1 over gamma dP dr times t over p. Let's actually stick this t over p here, t over p. So this is the adiabatic temperature gradient. Oh, here's a long one. So if we think about temperature versus radius, it's a decreasing function. So it falls off like this. And it follows the pressure derivative, which in the pressure derivative we know follows the mass. So we have an equation over here for how the pressure evolves with time, or with position, and it's just based on the mass because the pressure force has to be pushing outward. So the pressure goes down as you go out because the mass force is going down as you go out. So our temperature is going down as I go out. So now, the important question, and I'm gonna, let's see. So, so this is the adiabatic temperature gradient, and what we're going to show, and I'm just going to tell you that this is the solution, is that we get so whenever the temperature gradient for the bubble is larger than the temperature gradient for the star, that means it's down here. Then you have a stable star. But I'll show you that in a second. So let's just get there. So we're going to compare the adiabatic temperature gradient, which is this. This is the temperature gradient of a bubble that just goes up, because it just gets to be adiabatic, whereas the rest of the star has all four equations that it has to satisfy. So the star doesn't get to be adiabatic. It has heat flow throughout it. So the star has some temperature profile. A bubble is going to have some slightly different temperature profile. So let's talk about when something is going to float. So when rho bubble is less than rho star, we'll get convection. Right? So we can take a derivative of both of these, and we can say that d rho bubble dr is less than d rho star. I'm going to drop the star. Yeah, oh, sorry, I was calling it S. Let's leave it S. dr. So this is my criterion for stability. So let's track down what each of these is. So d rho dr for the bubble, we found over here because it's adiabatic. So this one is just 1 over gamma times dp dr. This is dp bubble dr times p bubble initial over rho bubble initial times 1 over gamma. And this is for the star. We'll solve this for the density derivative. So I've got a p over rho that comes over here, and then this comes over here. So this becomes d rho dr for the star equals rho for the star initial over p for the star initial times dp star dr minus p over t for the star initial dt star dr. So this is just this equation. And what I've done is I've been explicit about what's a star, what's the initial state, and what's the actual derivative. So we've got d rho dr for the star is equal to rho over p for the star, both the initial states, times dp dr, minus p over t times dt dr, which is just this. And all of this is just chain rule of ideal gas law. Just rearranged it a little bit. So now we can set these two things. We can write an equality here. So this is the adiabatic density gradient. So as long as this is less than this side, which is going to be rho initial for the star over p initial for the star times dp star dr minus p star over t dt dr star. The next assumption that we need to make is that we're always in pressure balance. So P for the bubble equals P for the star. So that affects this quantity, that affects this quantity, that affects this quantity. Also, all of the initial conditions are the same. Did I write something upside down? I wrote this upside down, pardon me. This part is upside down here. This is rho I over pi. So this bit cancels this bit, and yeah, we're left with 1 over gamma dp dr is less than dp dr minus pt over t dt dr. This is the actual. This is for the star. But everything else we can treat for the bubble, because everything else works for bubble. So we'll just solve a little bit, and we'll leave this on the right hand side. And then we get 1 over gamma dp dr minus dp dr is less than that, or now I'm going to change sign on you. So this is 1 over gamma minus 1. I'm going to change that to 1 minus 1 over gamma, so I pick up a minus sign, and that changes sign. Oh, I shouldn't change it there. I should change it here. Times dp dr, it's got a less than dt dr to the star. So this is the criteria for convection. But you can see that this is just equal to dt dr adiabatic. So as long as dt dr adiabatic is larger than t star dr, so that means as the bubble goes up, it's going to be hotter than its environment.
Yes.
Does that make sense?
Yeah.
That's
so
what this means. So
similar to how wind
Cooler than, sorry, I
works.
said that backwards. Cooler than its environment. Because there's an implicit minus sign here,
Well,
which makes this hard to get your head around because we're talking about equalities, but everything's negative. So this is negative, so this being bigger than this one looks like this. So this is the adiabatic. Sorry. This one has the bigger slope. It's more negative. This one, so this, sorry. This one has the bigger slope than absolute value. If I take the absolute value of this, dt
that's
dr adiabatic, then the sign changes. It's gotta be less than dt dr. So there's this sign change that is a little tricky. So this is talking about the slope. So this is the slope dt dr. Which one of these has, let's say that they're the same here, which one has the bigger slope, the one on the top or the one on the bottom? Yeah, the one on the bottom. I saw one of you say. So the one on the bottom has the bigger slope. It's negative, bigger value, so you go out a little bit more. The one with the bigger slope is the bottom. The only reason that I'm saying this so many times is because I forget how this is supposed to work every time. So the bubble, when it goes up a little bit, is going to have a little bit lower temperature than the surrounding area because of the gradient. So if you have a little bit lower temperature than the surrounding area, then it will start to float because it will take on heat and it will rise. So if it can take on heat, then it will continue to rise. So where did we write down? Oh, I didn't stop to ever write down this statement. So in this process, you can say that dt dr adiabatic is equal to this quantity here. 1 minus 1 over gamma dp dr. So that's this quantity here. So that's why I started talking about dt adiabatic is the same as this guy here. So this gives us our equation for convection. Oh, I wrote it differently though. I also know that dp dr equals minus GM rho over R squared. Right, that's what we got in the first one. So we can plug this into here and replace this dPdr with GM rho over R squared, and we're left with that top equation. Or we're left with the very bottom equation. So we use the top equation and we get the very bottom equation. So okay, so now I've got, okay, how many equations and unknowns do I have?
A lot.
Yeah, well there's 4 equations. And I've got 1, 2, 3, I counted that one, 4, counted that one. This one I'm gonna get, epsilon is an unknown, epsilon is something that I can compute. And T, I got 5 unknowns. Crap. So okay, do you see, does everybody see why there's 5 unknowns in this set of 4 equations? Or does anybody want me to go through that? R is not an unknown. R is my control. R is my knob. That's my independent variable. Right? So here I'll circle them. So my unknowns are P, mass, gravity is a constant, density I don't know, R is a coordinate. That's not something that I solved for, so that's something that I plug in. M we've already gotten, rho we've already gotten, R we got. Luminosity, rho again. This thing is computable, so that's not an unknown. Temperature is an unknown.
So that's a constant for the star.
It's not something that varies with position in the star. It's a function of temperature and density and pressure that you can then compute. But it's not a constant for the
It's
star.
not a constant.
Yeah. But it doesn't depend on density, it doesn't depend on position, except by the other quantities. So it's something that you can
Okay,
write
so it
down.
depends on radius and temperature.
It depends on, well, I wouldn't say radius, because it doesn't depend on radius. It depends on pressure and temperature. It doesn't have its own dependence on radius.
Isn't
That makes
it a
sense? Okay.
function of radius?
So- Epsilon is a function of the composition, the temperature, and the pressure, but it by itself is something that you can just compute. It's some function of these things that will just plug into here. It doesn't have any derivatives in it, and that's the important bit. It doesn't have. It's not part of the differential equation batch that I have to solve. Does that make sense? Right. So it's not a thing that I need to know. There's a machine. I just turn a crank on it. This is like u to the t minus p over the sine of p times t, right? It's some complicated ass function, but it doesn't have any derivatives in it, and it doesn't give us any new information because nothing else depends on epsilon.
So it's not a constant, it's just kind of there.
Uh,
We can compute it, and
yeah.
it's just kind of there.
Yeah, it's there. It's a quantity that you need. You can compute it, but you don't need to solve for
We
it.
don't particularly care about it?
No, you care about it, but you can't solve for it from this set of differential equations. It's a function that we got to plug in. Does that help?
Yeah.
So this is just a function that
Thanks, I
I'm gonna use.
hate it.
Okay. This is a function that we're going to use. Just like kappa is a function that I'm going to use, right? Kappa is not constant for the
Okay.
star. It depends on the ionization state of all things. But it's just a thing I can compute. I don't have to solve for it.
So, if it doesn't change throughout the star, depending on position of the star, why is it not constant?
Well, it does change throughout the star. It just doesn't have its own internal dependence on R. It does. There's
Okay,
no,
so it doesn't
When I
dep-
write down the equation for this, I don't have any derivatives in it.
Okay, I think
That's
I
the important bit.
took what you said in a different direction than what
Yeah.
you meant it. Okay.
So it's a number that you can compute, but it's not a variable that you have to solve for.
Okay.
And that distinction is subtle. It'll hopefully become clear, but I'm not actually going to build a whole stellar model. So we've got 5 equations and 4 unknowns. No. 5 unknowns and 4 equations. So we also need another equation. Okay, so we need another equation like PV equals nRT or something. That's not really perfectly accurate, but it's good enough for model building, but we need an additional equation. But this one's not a differential equation, so it's not a pain in our ass in the same way as the other differential equations are. So we need a fifth equation to close this, but this is how you get a star. So you get the temperature gradient from the convection, you get the luminosity gradient from the energy production, you get the mass gradient from the density, you get the pressure gradient from the mass and the density. So there's this coupled set of equations that you then don't solve by hand.
So when you have a convection star, is there any radiative that's happening in there as well?
So ultimately, both of these may happen, but usually one is way bigger than the other one.
So we just ignore whatever the smaller
You ignore
one
the other one,
is.
yeah. Yeah, so if it starts to convect, the radiation doesn't matter anymore, because convection is so much more efficient than radiation at moving stuff.
Okay.
There's an old phrase, never underestimate the bandwidth of a station wagon full of tapes, and this is what that's about. So if you just pick all the stuff up and move it, it's a lot faster than letting it trickle through all the atoms by itself. So, so that is it for convection and our 4 equations, except for that epsilon. So we'll talk about that epsilon for a minute, but how am I on time? I have 10 whole minutes. So what do you do with these? So you plug them into a computer, and so these are, and you get the computer to solve all 4 of these simultaneously. It's not possible to do it by hand. There may be cartoons that you can write down. There's one solution that you can write down to this that I may do on Wednesday, but I haven't decided.
So we're not solving these. We would take a computer program.
That's
to do
right.
this?
So you get a
Okay.
computer program to then iterate over these 4 equations. But we want to talk about them because what goes into those computer models is important.
Mhm.
Let's talk more about burning. So, okay, pardon me, where's my notes? Is there anything else that I need to check in with? No. All right. So I'm going to talk about energy production. So the first thing I'm going to talk about is gravity. So the most obvious thing, so I have this star, and energy is coming out of the star, right? So energy's got to get into the star to come out, right? So, okay, let's talk about the binding energy of the star. Let's assume first that it's gravity. Let's assume that the stellar energy source is the gravitational energy of the object. So I have this binding energy, which is minus g m over r squared. Or, I'm going to make you do this for homework. Sorry, this is gm rho or something like that. If I have a uniform sphere, so that rho is a constant, then this turns into minus 3/5 g m squared over r. Oh, I'm sorry. Why did I write an r squared here? Asshole. R, just r. That's the potential. The force gets the squared. The energy does not get a squared, because remember the force is the derivative of the energy. All right, so so this is true. This is how much binding energy the star has. So we can pretty quickly, oh, and this is not little r, this is big R, this is the radius of the star. So if we're doing this for the sun, this is going to be a solar mass and the solar radius. So this is the binding energy of the sun, thereabouts. So I want to know how long my thing can last for, so I need to know how fast I'm going to suck out all of this energy. Okay, so what the book does is says, well, this is virialized. This is U, 2ke equals u. But regardless, the book goes through, sorry. I started talking about a thing and then realized halfway through that I don't actually want to talk about that thing. This is the bindings, this is the energy that you have. The only difference between what I'm gonna do and what the book does is a factor of 2 that I don't care about. So this is the energy of the star. So the time scale to get rid of all of the star is E dot over E. Does that make sense? Does that seem right? Look at it. Think about units. What are the units on this?
Energy.
Per?
Second. Area.
And what's this? And this is, what are the units on E?
Joules per second.
So this is gonna be joules per second,
Joules per second.
and this is gonna be joules. E's in joules, right? E is in energy, right? So if E is in joules, E dot is in joules per second. So what are the units that I've got right here? This is upside down. What's that? Yeah, so this is gonna be just for time, but it's upside down. I wrote it upside down. E over E dot, this is in joules and this is in joules per second. So this gives me a time scale. I do that every time I have to write down a time scale. I always write it upside down. I don't know why, because I'm an idiot. So when you want to find a time scale, you need to think over its time derivative. That gives you the time scale for all the energy to go away. So if you do that, we have energy. And what's E dot? This is for the sun.
Change in energy.
Yeah, so it's the change in energy for time. If I'm going to plug in a number, what number would I get? What's the change in energy for? Wait, what's that?
Yeah.
The intensity or luminosity?
It's the luminosity of the sun. So this is just 3/5 times g times the sun, mass of the sun squared over the radius of the sun over the luminosity of the sun. This gives you the lifetime of the sun if gravitational energy is the main energy source. Does that make sense? For the most part?
Yes.
This is about 10 to the 7 years. That is not enough years for the sun to exist.
So it's not gravity.
This is not gravity. But we didn't know that for a long time. I mean, Kelvin and Helmholtz sorted this out in the late 1800s. So if you instead say that it's nuclear burning, and let's say that 10% of the sun is going to burn, so 10% of the hydrogen is available, and I get 0.7% of the hydrogen when I burn it. And this is a thing I can do. I can burn hydrogen. I can do nuclear fusion of hydrogen in the lab, so I know exactly how much energy I get out. All right. So if I have 10% times 0.7 times a solar mass times c squared. So if this is the energy that I use, this is the total nuclear energy density, or total nuclear energy content.
Sorry, can you, so 10% is the available fuel that gets burned down,
Yeah.
right? And the 0.7 is the output energy,
Yeah, this is the efficiency.
efficiency.
So yeah, you can think about it as the output energy relative to how much energy you actually have. So when you burn something, you don't ever lose a whole proton, you lose some part of it. We'll talk about this 0.7% in a second, yeah.
Oh, never mind, I answered my question, that makes sense.
Sweet. So 10% of the whole star times 0.7% efficiency times mc squared gives you a much larger number. So this divided by the solar luminosity gives you about 10 to the 10 years. And that's long enough, because that makes sense. There was something, there was one other thing. Yeah, yeah,
Is that max times speed of light speed?
yeah. So one last thing before we part ways. The mass of a proton MP. The mass of an electron is ME. There are numbers that go with these, but as you may have gathered, I don't like numbers. It's MP, that's all that matters. What is the mass of neutral hydrogen?
Mass of one proton and one electron, plus their binding energy? Yes.
Plus their binding energy. So if I take a hydrogen, so hydrogen weighs more than a proton and electron by the binding energy of the two things. Does that make sense? No, I'm sorry. Less. It weighs less. Why does it weigh less?
It hates you.
Because the binding energy is negative. Right? It hates me too, that's also why. Yeah.
Is it a reduced mass?
No, this is the total mass, the actual mass of a hydrogen.
Oh yeah, but like is it like the binding energy?
This is all the binding energy. If I put a hydrogen in a little tiny scale, you can measure this difference. What is the equation? I'll get you questions in a second. Let me ask one more confounding question. What is the energy of hydrogen in the first excited state?
It's like,
The same thing, minus 10.4.
yeah.
Because that's that binding energy. So as I go to higher energies, you'll see I get closer and closer to the mass of just the two things by themselves. This is where the energy comes from. This is it. This is where the mass comes from in nuclear burning. It doesn't actually come from any particles being destroyed, though some particles are created and stuff, but the net number of particles is not destroyed. It's all in binding energies.
We're not dealing with neutrons here.
Well, no, we'll deal with neutrons too. What's the mass of a neutron?
Same as a proton.
It's the mass of a proton plus the mass of an electron plus their binding energy.
And we don't account for strong force.
The strong force is the binding energy.
Okay.
That's why I just wrote down binding energy rather than anything else.
Okay.
And it's also negative, so that's gonna be lower, because it wants to be together. Yeah,
Right.
Binding energy is always negative.
yeah.
Okay.
Binding energy is always gonna be negative, it's always gonna be gluey.
So
If it's positive, then it's gonna wanna leave.
what does the binding energy steal from?
Just winks it.
Mass isn't conserved. So it doesn't steal from anything. You just get more mass. Mass isn't conserved. Mass just gets to go up. It's not stealing from anybody, you just have more mass now. At the expense of the energy. So it steals from the energy. So the potential energy looks like this. So you steal mass from down here. So you pick up mass when you go down here. Does that make sense?
Yeah.
Alright, so we'll go through details of the burning and some other stuff on Wednesday. And then there's no class on Friday because veterans. And what's that? Okay, anybody have any last questions before I go? Oh, I'm sorry. Does that help? The only velocity that matters is c, so that should be 1.
Whoa, 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 calm down.